Alright, in this video we're going to talk about math induction, and I'll just show you an example of how to do it. So let's just get started here. So this is a table with 4 people seated around it. So one table, 4 people. So we'll start so you can kind of see what's going on here. And we'll call this N and this S sub N. So N is the number of tables, and S sub N is the number of students per table, with however many tables you have set up. So number of students. Kind of ran off there, sorry. So N number of tables, S sub N students. There's one table, 4 students. So let's continue this pattern, and let's say we can only go to the right with our table. And so now here's our table with 2 tables, and it has 6 students. All right, and let's say this is the only way we can continue this pattern. So we can't go down or up or left, any other direction. We're just going to keep going right each time. So every time we add a table, now we've got 8 people. And so that's our pattern. So in table form, it looks like this. So far we've got at one table we have 4 students. At 2 tables we have 6 students. 3 tables we have 8 students. Let's imagine kind of this infinitely long room. That's what you have to imagine. And we keep doing this pattern. Keep making these tables. Keep adding tables, adding students. And so stop and think about what's your next number in here. It's a fairly easy pattern. You know what? If I go to 4, how many students do I have? If I go to 5, just pause the video for a second and think about it. So the first pattern you might have been thinking about is the recursive pattern. You know, once you have some numbers in place, real easy to continue that pattern. So we notice there's a difference of 2 each time. So the next one would be 10, 5 would be 12, so on. That's thinking about the problem recursively. And there's a formula for recursive definition. So whenever you have a formula, so this is kind of the witchcrafty part of math, and hopefully I can kind of demystify it for you a little bit. My students have the most problems with this. So let's just talk about the terminology. So this subscripted 1 here at the bottom, I dropped it down. We call it subscripting in math, and typically that's just to show position. So this says to me students at one table. Students at one table, S subscripted 1. The first set of tables would be another way to think about it. And we know that that's 4. So this is, when you define something recursively, you have to have a place to start. Then the rest of the rule would look like this. If you wanted to continue forever and continue adding tables forever, so S subscripted N means we could go to the 20th table, or the maybe the 6th table. You can pick whatever number of tables you want. If you think about the rule, it's your previous term plus 2. Excuse me. Mathematicians have a way of saying previous term. What they do, the previous term of the S sub N term is the S sub N minus 1 term. And so that's previous term plus 2 is our rule. So all this means is a fancy way of saying, and a short way of saying, an abbreviated way of saying previous term. So don't let that scare you. So maybe it would help to use this formula. So again, just to recap, recursively you have to define your first term, and then we defined it as our previous term plus 2. So let's say I wanted to find my 6th term. So my sixth term, well, my previous term to the sixth term is the fifth term. You know, it's s sub 5. And we're going to add s sub 5 plus 2. Well, we know s sub 5 is 12 plus 2, so that's 14. So when we have 6 tables, we have 14 students. So that's recursively. The problem with recursive is you could continue on forever and ever. If you wanted the 100th table, you got to go find the 99th. So you're going to have to continue this thing clear out to 99, which is a pain in the butt. So that brings us to explicit. And maybe you came up with this first. Some of my students do when they come up with the idea for this this pattern. And I'm going to be very specific. This is when we add 2 each time in a sequence. That's called arithmetic. And there's a formula to find these quickly. Now, there's lots of ways to do this, but beans, we know it's arithmetic. Why not use kind of a quick and simple trick? And the quick and simple trick is this. You take the difference, the common difference, times n minus 1 plus your first term. This always works for arithmetic sequence if you have this information. So in our case, and we'll use the same notation. So students at n equals, our common difference in this case was 2 times n minus 1 plus my first term is 4. So this is the explicit formula. And I'm going to simplify this a little bit just to get us into something a little nicer. Get us into a form of like y equals mx plus b. You might be used to seeing it that way. I'll distribute my 2 through, add the negative 2 and 4 together, so we'd have 2n plus 2. So that's the simplified version of this explicit formula. So now what's nice is if you want the 100th term, you don't have to find the 99th term. You can just plug it in. So it's the 100th term in this case is 2 times 100 plus 2. So if I had 100 tables in a row, I would have 200 plus 2. I was going to say 202 and I wrote it out, but yeah, we'd have 202 students. And we could check the 6th term just to make sure it matches. So at 6 tables, you have 2 times 6 minus 1 plus 4. Oh, I went back to the original one. My brain shifted back. But anyway, so 2 times 5 plus 4, 10 plus 4, 14. Or you could have used the simplified version, 2 times 6 plus 2, or 12 plus 2, which is 14. So either one works just fine. I don't know why I shifted back to the unsimplified version. But so there's, at 6 tables we have 14, at 100 tables we have 202. That's the advantages of an explicit formula. But how do we prove that these two are the same? You know, we're clear into 8 minutes in this video and I haven't even shown you math induction yet. Because I think it's important to set all that stuff up first. So here we're going to go ahead and I'll show you the method that worked best for me. I set this up in a table, and this was, when I saw this, I didn't understand math induction until I saw this. But you set up your recursive, number of tables will stay here, recursive here, explicit will go here, and then this last column is just to verify, is it true or false? So I have a little question mark, so you'll ask yourself, is it true or false each time? So with math induction, you have to show that it works for the first term at least. First couple is even better. So we know in the recursive formula, when we had s sub 1, we know that was defined as 4. That was our first, that's our starting point. In the explicit formula, we'll test it and see if it is indeed 4. So S sub 1 is 2 times 1 plus 2, which 2 plus 2 does equal 4. And I'm going to switch to a different color so we can see it. And is that true? Yes, that's true. So we'll check that off. We've shown that the first term is 2. And I'm going to do just a couple just to make sure. So number 2 then, S sub 2 equals your previous term, which is 4 plus 2. So that would be 6. And if we plug that in to the S sub 2 formula, the explicit formula, that'd be 2 times 2 plus 2, which would also be 6. And so it's true. The recursive and the explicit are true. And if we go 3, this will be the last one I do. So S sub 3 equals your previous term, which is 6, plus 2. Again, that's 8. And if you do it on the explicit side, 2 times 3 plus 2 also equal to 8, not 6. So 6 times 6 plus 2 is 8. So there we go. We've shown it's true. Now imagine continuing this on and on and on forever. We can show this all the way. These will be true all the way down. We could keep showing it and keep showing it and keep showing it. We'd eventually get sick of doing it, and it wouldn't prove anything. So what we do instead is we go all the way down to the k minus 1 term. So we'll look at that information. And we go, and then the next one is the kth term, or if we kept on going to the next term, the very next term would be the kth term. So if recursively, it would look like this. So S sub k minus 1 equals S sub k minus 2, the previous term, plus 2. That's probably a wild one there for you. Sometimes it is, sometimes it isn't for students. And so also for the explicit, S sub k minus 1 equals your 2 times k minus 1 plus 2. Sorry, I ran over a little bit. But that's going to be important. And I should maybe go over that with a different color so you can see it. I hate that I picked blue again, and I don't quite give myself enough room on a 480p. Doesn't give me quite enough room. But that's very important. So we assume that's true because we went forever and ever and we kept going down and kept going down, and every time we plugged in a number, it was true. So we're going to use that. So here's your recursive formula now for this one. So we have to show this. So S sub k equals your previous term, which is S sub k minus 1, plus 2. And we want to show that that's equal to S sub k equals 2k plus 2. We have to show this. This is what math induction is all about. So we're going to use a little bit of algebra to show that these are true. So we're going to show this. It's not true yet, but we're going to show it. And what's cool is since we went to the k minus 1 term, we can use a little substitution. I'll go to black here. Notice on the explicit side, we have the students at k minus 1 table equals 2k minus 1 plus 2. So we have this term right here. We have S sub k minus 1 for the recursive formula. So we're going to use substitution and just continue this down. So we know S sub k equals, and I'm just bringing everything straight down, and I'm going to use substitution to plug in that S sub k minus 1 in the explicit side, which is 2 times k minus 1 plus 2. That's bringing that down. And then plus 2 brings down the rest of it. And then we're going to simplify that. And when we simplify that, we'd have, if you distribute through, you'd have 2k minus 2 plus 2 plus 2. Minus 2 plus 2 is 0, so it simplifies, s sub k simplifies to 2k plus 2, which is what we wanted. There it is. S sub k minus 1, we just showed that it's true. The recursive formula and the explicit formula match forever in this case. And so what you want to do at the end is just give yourself one statement that shows what you found. And so this is a nice way to write it. So this establishes the truth for all statements s sub n equaling 2n plus 2 for all n greater than or equal to 1 by mathematical induction. And just some final notes, you could have also used, I used the subscripted notation, but you could have just as easily used function notation. It's really no issue. You have so much going on here. I like the subscripted notation just because it looks cleaner, and that's why I chose it. But definitely this and this are used to mean the same thing in this context. So function notation, subscripted notation, they both work equally as well and are used equally in the math world. So that's another thing that students have a problem with. So hope this all helps you, and good luck, and see you next time.